So this is just really a simple definition that we're going to look at, and more so an effort just to gather up again, reason to gather up and take a look at this fun little piece of software. So what we're doing with this particular, in this particular definition is we're using Ladybug to run a couple of solar analyses in order to determine the usefulness of shades given some orientation. What we were going to go over was this definition that I put together and will make available to you all. That primarily uses Ladybug, the legacy version of Ladybug, to open up a weather file that it can find online. If you plug in a URL, pulls in that weather data, creates a sun path for you to, I guess, understand the rise and location of the sun throughout the day, the altitude and azimuth. And then using that sun path and information gathered about the sky conditions that it pulls from and assembles using the weather file data, also conducts a radiation analysis. And this can help determine how much heat a particular spot is going to receive. This analysis down here is a sunlight hour analysis, and it will indicate how much sunlight a piece of area will receive. In this case, we're actually going to be working in metric. I apologize. So when I say area or piece of area, this unit of area of space is going to be in meters squared and kilowatt hours. So sorry about that, but that's just the default for Ladybug. There's a number of extra components that they make available in order to do conversions from imperial to metric. But I just didn't want to clutter up this definition with a bunch of bespoke or discrete components like that. So let's see here. So the reason why we're looking at these two, trying to think of a balance or something. So when thinking about performance or what it is to optimize something, you're always, or typically, you're not always looking to increase the good effect, but oftentimes you need to also quantify and target a decrease in negative effects. And it's it's identifying where those two increasing benefit, decreasing some negative effect, increasing the positive effect. At a certain point, those two will cross, and it's at that intersection that starts to point out a combination of parameters given some scenario where the optimum value would be if you were to, if you were thinking about increasing the benefit of sunlight, you keep on going up, but at a certain point now heat gain starts to become a real problem for you. So how much sunlight can you let in without heat gain becoming just an issue? It would be right at that intersection of those two curves. So sorry, I'm drawing with my hands, but I hope that all makes sense as far as just what it is to optimize something, optimize the performance of something. It's not just to improve the positive, but also reducing the negatives and comparing the two. So when we're doing these kinds of studies, we'll take a look at the sunlight hour, availability of sunlight, as well as appreciate how much heat that sunlight is bringing in. And it's when the sunlight is bringing in the heat that these shading elements can become very useful. They'll, in cases, bounce or absorb the heat depending on what they're made of, and then bounce that light into space, somewhat diminished in overall light levels, but still, it's better than nothing. So we've got over here some test geometry that we're going to use just to run some of these analyses. I'm going to hide hide this stuff over here. And so I'm going to try to, I guess, move through a process where you would maybe use this in a real life situation. When you're modeling and using Grasshopper, it's often the case that you're, not everybody's going to be using. They want to be able to control the logic or being able to democratize that logic or the design, the parametric design, finding ways to do that, or at least accommodating others' input is an important aspect to making this tool, Grasshopper, particularly useful, to be able to put this power into other people's hands, or at least to accommodate that kind of input. For a long time, I used to just build everything inside of Grasshopper, but then started realizing the usefulness of hosting these definitions on native Rhino geometry, so that way other people can make changes to the geometry and things can just automatically update, rather than everything being custom and tightly integrated into one another, or responsive in a way, but all inside of Grasshopper. So what this definition takes in order to get going is, so we'll start off with an analysis so that we can understand if we even need shades here. This is, meant to be a building that my coworker gave to me in order to run an analysis on. There are opaque geometries here and transparent geometries. Obviously opaque geometries don't need shades. So we're going to focus in on these, what are representing transparent geometries or windows, curtain wall, other types of glazing. And these will be our three-dimensional inputs.
Question real quick.
Yeah.
Sorry, with the opaque and transparent, is that defined Rhino side or within the Grasshopper script?
These are inside of in Rhino, yeah. So that way, anything that changes on this side, the script will update the shading strategy.
How do you define a surface as transparent or opaque?
In Grasshopper or in Rhino?
Either, however you went about it.
Oh, I guess what I'm thinking is it's more conceptual. So I've taken this, these layers are on a layer that has certain properties. These geometries are on a layer that is imparting properties onto them. So these are just simple surfaces. There's 4 surfaces here that are on a layer over here called transparent surfaces. I've made them blue. If I were to move them to opaque surfaces, they would automatically update. Additionally, in addition to the display, their display color and appearance, there's also a material column where we can be specific about its rendering materials and perhaps thermal properties. But so again, conceptual.
Okay.
So these are really, just surfaces in Rhino, and we're going to use them as inputs in here. And it's in as much that we're considering them transparent geometries. We'll just say that they're going to represent the size and location and orientation of our windows to be. Oh, I guess I should mention, yeah, this is kind of a very much SD programming level exercise here. So the controls over the shading design is not going to be incredibly robust. You won't be able to do anything you want, but you will be able to understand what is an appropriate sizing, both in depth and spacing in between shading, whether it's horizontal shades or vertical shades are more beneficial given some orientation. So we'll apply shades to this box and just to those transparent surfaces, and try a couple of different permutations of that and see which one works better. But first, so I want to kind of go through. So this is going to be the this is a native, or not native, but a Ladybug tool. It's called Ladybug Shading Designer. It's inside of this is a just an easy small program that's going to create the shading design.
I'm really interested.
If there were interest, you can always break these apart or reverse engineer them in order to get them to do more maybe ambitious things with their shades, but this will be rather normal. If I turn it on right now, you'll see we've just got little shades right now. We're in feet. I'm going to meters. Wow. So we're in feet, so this will mean the depth of these are right now 4 inches, a quarter of a foot. So they're 4 inches deep. The distance between is 1 foot. If we want it to be, if we want it to be half a foot, that's easy. But the real question is that good? Is that a good thing for the overall performance of the building? So this will be the thing that we're really going to be playing around with. And then using those analyses on the other end to appreciate how those changes in the design have real world performance impacts. So, yeah.
I'm just curious for that last definition that you were kind of going over. Is there like a Z dimension or like a thickness of that material or the shading, I should say?
No.
Okay.
Well, we could do that. So what comes out at the end of this is just a normal grasshopper geometry, untrimmed surface. So we could take that surface and extrude it and give it some thickness. So this will be a foot thick. Once I get this in there.
I'm just wondering if that actually changes any of the kind of output data, given that there's no like Z or depth dimension.
It certainly will. It certainly will. And I think maybe for that reason, maybe thinking, well, it could be useful to identify what that material is, but if we can just kind of get close to where it needs to be, and nothing is an exact science. And with climate change being what it is, maybe we should be designing these for some near future catastrophic environment. But I'm sort of trying to just play it down. But I guess really what I should say is that this is a very much like a programming approach to just understanding shades and SD and at SD at schematic design, you maybe wouldn't know exactly how thick something like this needs to be, but you would know how much an approximate idea about ratios. I think ratios are a really great thing to distill in these types of exercises, because inevitably, invariably, your project will change, and you need to be able to define rules about these systems. And so when somebody starts to mess around with the placement and the sizing of the windows, you can easily communicate to them and verify that whether or not it meets a certain ratio, which is like 30%. Window to wall ratio is a great example. So in most environments, 30% is ideal, but that's a rule of thumb. It's not 30% isn't ideal when you have some surface or some facade that's more protected, perhaps even by itself, self-shading type of situation. So this method, or what we're seeing here, will show you how you can analyze very local conditions instead of having to simply apply those rules of thumb. So we can say, well, let's get into this a little bit. Did I just tiptoe around your question, or did I address it in any sort of way?
No, you totally nailed it. You got it. Thank you so much.
Okay. Yeah. So let's go ahead and keep on rolling through here. I think that this is a pretty cool. This is the really interesting portion. I mean, yeah, I guess maybe not really all that interesting. This is the climate data portion. For decades, they've been collecting weather data every hour, every year, every day, for decades, since the 70s, I believe, usually at airports, and all of this is made available through your tax dollars at work, the the Department of Energy, United States government collect this data and make it available online. And Ladybug has made it easier to access and pull that weather data into Rhino and Grasshopper for use and analysis. And it's a very simple analysis. It's more a calculation and a geometry problem than it is an actual thermal simulation like you might see in more sophisticated programs. If you want, that kind of analysis, Honeybee is a really great way to reach out from this environment to those more robust, more capable kinds of programs. So again, this is very simple, just kind of getting an idea about what kind of designs we should be entertaining during SD in response to the climate. Ladybug, there's the component that holds all of the programs, all of the information and actions. Everything's written in Python, and so this component loads it all up. This always needs to be on the canvas in order to run any Ladybug component, because by putting it on the canvas, it loads up all those scripts that they wrote in Python to your hard drive. And now it's accessible to all of these other components. You can double click into them and see, if you really wanted to, see what Python looks like and what they're doing inside there, if you were so inclined. So I'm starting a project. I need some weather data. Where do I go? This is a button. If you press this button, it'll jump to Ladybug's website, where you can navigate using their nifty interface to whatever location you so choose. Who's from the farthest place? Who came the farthest tonight? Does anybody have any place they'd like to see in particular? I could pick Portland, but it's boring. All right. I'm going Florida. I'm going Gainesville. So what's nice about this is that you don't have to download any files in order to start using this the data, but you can just click that link right there, copy link to clipboard. And so we've done that. I've clicked it. It's on my clipboard. Now I go back to Grasshopper and simply, oh no. Oh no, something's frozen. Does it ever happen where you can't interact with these things? Like somehow something just stops working and I can't select anything. All right, so I'm gonna have to start this over.
No.
Sorry.
Just when you're being watched.
Nathan's here, everybody. Here he is. All right, let me real quick switch this back over. So I say no. I'll just close it. All right, now we're going back in. So screen, test that. Got. Install this step. So this runs a couple of calculations, this particular definition right before it starts. So it does take a little bit of time to open. Right now it's figuring out sky conditions based off of the last weather data file it was provided. But once it opens, I still have that link in my clipboard. Yeah, so this is the circle version of our example projects tonight. Might as well stick with it since it's there. But I'm going to turn off those shades. All right, so I got that thing in my clipboard. It's Gainesville. So all I got to do is just copy and paste it. Once I've done that, it's going to rerun and pull in all that data from the internet. And once it's done, then we can start to tear into it and see what's up. Oh, yep. Nope. Just running scripts. I hope it didn't freeze on me. Okay. Now I'm nervous. Okay. And now I'm being neurotic about it. Okay. So it's pulled in all that data. What that data is specifically is, did you know there's 8,760 hours in a year? And the only reason I know that is because there's 8,760 data points here. If you were to, this component is pulling apart all of the relevant data that's stored inside of that EPW file and providing it to you in a way that you can understand. This information here is just dry bulb temperature. The temperature is recorded in degrees Celsius. And it's hourly. Line 5 says it's indicating what month, day, and hour this record starts on, and then line 6 tells you the same, but when it ends. So we've got a whole year of temperature data streaming in. We also have humidity data, wind speed, wind direction, and then we've got radiation, normal radiation, horizontal radiation. These are, we'll use some of this information for our radiation analysis. In addition, there is a statistics file. So there's some pre-processing that's also pulled in as well. Down here is the last kind of setup group where you get to set the analysis period. Right now, we've got it set from day, from month. We've got it set for January 1st at 1 o'clock in the morning, and it goes until December 30th. Well, we just change that real quick. 31st. That way we have everything. And now I've changed every time I make a change, it's recomputing everything that's downstream from here. So forgive me I could lock the solver and move quicker and respect your time. But it's done. It's run the whole went through the whole EPW file based on the analysis period that we just provided it. And it's done a couple of things. One of them is it's generating this Sunpath diagram, which is pretty, I don't know, hard to look at. This is Gainesville. And it's got a lot of sun and sun positions that are being displayed here. I think one thing that these individual sun sizes are a little bit too big. So 2 sounds big, so I'm going to make them 0.5. And that might make this a little bit better to look at. But so there's visualization and analysis. And this is, a great version of, a Sunpath diagram is just a visualization. Analysis is when you start to pull it apart and I guess understand something, or at least intersect it with a need. Or so what I'm going to do is put in a conditional statement here so that the sun path, depending on what your question is, there's blue ones, which are colored that way because they're indicating the dry bulb temperature of the time of year in which this sun position sphere is being representing. So in Gainesville, you can see it's cold in the morning down here, and then gets much hotter throughout the day. And well, I don't need to explain Sunpath diagrams to you, but what's neat about this is that you can filter out sun positions that you don't care about. So there's no when it's low in the sky, when it is cool, something like radiation and heat gain is something that you'd actually like. So looking at this Sunpath diagram, I'm considering, early in the morning, winter day, I probably want to orient it a little bit to the southeast, just as a start, before we even get into the Sunpath diagrams. Andy? Or did you have a question?
No, I'm good.
Oh, okay. Sorry. I thought I heard something. Cool. Yeah, so depending on what your objective is, if you want heat gain, these are the sun positions that you're going to isolate and test for. If you don't want heat gain, or where you don't want heat gain, which is during the summer, you can see all these yellows, which are indicating the sun's position and what you'd want to try and shield your window from. So we've got all these positions, we've got all these vectors. So I want to filter out, as a starting point. I'll come back to that actually. Let's run these analyses. All right, so we've got the sun positions. What's cool is you can filter out, put in an argument like, just show me the sun position when the temperature is over 80 degrees. Those are the ones that I want to block for. So we'll jump there, but I just want to run these quick analyses here. What these are going to do, this one's going to be a radiation analysis, and this is something that I guess you would consider bad in the summertime and good in the wintertime. And then the sunlight hour analysis is good all year round. What we're going to do first is run the sunlight hour analysis. It's already getting streaming into it geometry. The geometry is the surfaces that we have set up or indicated like way over here. They're actually going through, and I'm creating a mesh just because those run faster. I'm using Ladybug. It's got the sunlight hour analysis. So it's got the geometry, which is just the windows, and that's about it. There's not really a whole lot of self-shading that's going on here. There's a little bit of a lip, but it's kind of negligible. So right now, the only thing that's streaming into here that was way more, 36. It's connected to the wrong thing. Well, that's good. So we've got it. Oops. All right. There's that. Now we got our windows going in there. There should be just 4. There we go. So there's 4. 1, 2, and 3 and 4 all the way around. Each oriented east, west, north, south. Sunlight hour analysis. Little legend over here. I'm just gonna turn this Boolean. Double click it to get it to start running. It's running now. It'll take it a second. It's just churning through all the data. As well as using the sun path and all the vectors for the whole entire year. It's shooting them right now at the surface and seeing how many times, like which ones get hit, and just calculating, counting them up. And now it's trying to figure out how to plot this. It's connected to it should be, you'll see that it will visualize its exposure to sunlight on the surfaces once it completes. So yeah, just laser sound effect. Laser sound effect. I could have sped this up if I had narrowed the scope of our analysis period, which I'm going to do afterwards, after this finishes. Lasers.
So while this is processing, you have the geometry input is those 4 surfaces,
Mhm.
and all of those are run together as a group, or are they isolated individually?
Individual surfaces.
Okay, because I was just thinking like, okay, let's say you have just these vertical planes, and let's say you have another group of, hey, what if we put skylights in the space, and you'd be able to then run those separately?
Mm-hmm. Yeah. Or add them to the group of any transparent surface in the model would be converted to or I'm sorry, any geometry in the model that's intended to be a transparent surface would be included in something that would provide light and be worthy of analyzing. Yeah, you just group it into the pile.
Yeah, because the original input, are you pulling from data on that layer versus individual objects?
I wish this thing would stop running. Like to hop over. It is being very deliberately selected. So you would drop a component. It's a surface component. So and then you would set the geometry to that component. Elephant. And then they got geometry pipeline that's native in Grasshopper that I like to use a lot, so that way I can just tell people like just draw on a layer like this, like that's named this, and anything that you put there, it'll get analyzed and loaded up into Grasshopper and churn out something.
Nice.
But yeah.
And maybe this was like my last question. Maybe it's not pertinent at this SD phase. I mean, yeah, I don't know. But do you think it'd be appropriate in this phase to generally have the context, meaning like general squares of other nearby buildings, or is that maybe a next step or something?
No, it would be completely. It would be very important, even more so important than trying to analyze your own design. It would be important to use these same kind of tools to understand the context. If I'm just designing in a vacuum and expecting, that 9-story apartment complex next door won't impact my access to sun, and so modeling those things, and even modeling the like development and height limits, and understanding what are your projections to solar access on a given piece of property. What can you expect your neighbors to do, and to guard yourself against that, or at least prioritize things that are less vulnerable to developments you have no control over.
If we had, in a hypothetical situation, if we were running this analysis and you had like a big square that was a different building or something like that, would this analysis kind of account for, like, would it limit the amount of data that is being blocked by that context, if that makes sense?
Ask me that again. Sorry, I realized I started reopening this.
Someone could probably phrase that a lot better than I did.
I was just a little distracted. Sorry.
If you had hypothetical, if you had the context of just a square, another building or something like that, and you ran the same analysis that you just did, would that be representative in the outcome?
Yeah. There's we have the ability to put in some geometry that will represent the context and have it impress itself in the data and how this building is receiving light. It's in the same way that we might represent context and build it in opaque surfaces, and these shades will all come together as just context and things that will block light from reaching the surface.
That's awesome. Thank you.
No problem.
To take that a step further, it made me think of what about trees adjacent where you would get block in the summer, but not in the winter,
Mhm.
and how complicated would that be to include in the script? Because I feel like you could do some sort of, I don't know, ellipsoid to represent a rough tree canopy, but figuring out like seasonally. Well, you also it was coniferous versus deciduous, and maybe it's getting a little too complicated right now, but that'd be.
No, those are exactly the right questions to be asking. As far as those go, usually, hopefully you would have a landscape architect that's consulting, and you'd be able to ask them questions about the description of their canopy and their shedding cycles if they are deciduous, and including those in your calculation certainly would provide a lot. Vegetation has a lot of benefit given that it is responding to those temperature cycles that you're also responding to. So you probably could get a lot out of those, a lot from those vegetation. They do need to be close-ish, but you know, that's, I guess, if the tree isn't going to undermine, if it has good coverage and it's not going to undermine your structure, then I can't see all the short. I can't see why not. There was a project I worked on where I got to do some solar analysis thinking about trees, and honestly, it's not too complicated. You don't need a tree to be all, you know, like mesh and have all individual leaves, you know, all intricately modeled in order to get an idea about its impact and how it will, its impact on the solar analysis here. Instead, you could really just have a silhouette of the tree, because really we're talking about rays and this is all very much two-dimensional. So going online, finding a tree silhouette in vector form, bringing that into Rhino, making it a solid and calling it, you know, context, and it'll, you know, be one of those pieces of geometry that shields the window. So,
Hey,
all right.
Yep. I was just going to add to that, Jacob.
Please.
I've done some analysis as well. And for trees, I actually just used a mesh from Inkscape assets. And that was a really easy way to kind of replicate it.
Yeah, that's a good idea. Inkscape has made so many different commonly modeled, assets, you know, modeling assets, and made them available to so many, and it's so useful. Having those renderings are getting good nowadays, just because it's like properly entouraged, and we've got TVs and remotes, and everything's looking really convincing. Those meshes, I guess I'm wondering how they would interact with with what Ladybug is doing, because I just had to restart my this program because it seemed that an analysis period for one full year and running a Zoom is too much, or maybe I just got impatient. But what it's, you know, so a mesh has a lot of faces. If it's an intricately modeled mesh, which sometimes those Inkscape models can be. Ladybug would still be shooting sun vectors at that mesh and trying to understand if it's hitting something, and the more geometry that it has to look at and analyze, the more time it takes. And so keeping it real simple can get you farther faster. But as you know, when you get to the point where you're looking at when you're putting the final touches on the design, how close the trees are, what their makeup is, the thickness of the shades, all of those things will, you know, find a home here. I just wonder, I guess, it's a great idea. The thing I wonder about would be just like, will it take a long time to compute those meshes? But thank you, Chris. Thank you.
Yeah, no problem. And
Yeah,
I totally get what you're saying with the times, and you know, I don't have any kind of comparative, you know, feedback for that. But you know, they are kind of just like simplified meshes. They're kind of like, you know, inflate. They just kind of look like the tree. So
right.
the amount of surfaces weren't like incredibly, you know,
Okay.
like large. But
Mhm.
I totally get what you're saying, you know, just like even if it was like in Revit, they have those like 2D looking trees that,
Yeah,
you know, can represent the size of a tree, which definitely helps.
right.
I just brought up the Enscape one because, you know, as you're going through a design and you already have those assets there,
Yeah,
just kind of using them.
yeah. No, that's a great idea. I hadn't even considered it or thought of it before, and probably will use that in the future. But yeah, the thing I worry about geometry. But that's great. Yeah, it's yeah, trying to find like model or the accurate dogwood in the Illustrator. So oh, go ahead.
Oh, I was just going to agree. Yeah.
Yeah, right on. So this thing was taking a long time. I reopened it. I changed the analysis period while we were here talking. So I hooked it from here to the stat file up here. And this is pulling from the weather file above, a typical autumn week, what it's determined to be a typical autumn week, given this particular climate. In other climate zones or locations, the typical autumn week would be a set of different days, but in Gainesville, it's August 20th at 1 o'clock in the morning to August 26th. That's the typical autumn week. And so instead of running a whole year for the Sunpath and all these analyses, we'll just do the 1 week so we can speed up. All right, we were looking at the sun hour analysis. We determined geometry was actually connected to the wrong thing. So this test geometry, which is our surfaces, which is our input surfaces, representing transparent geometry. Just that, that's all it is. Just 4 circular surfaces. I'll hide that. That's our test geometry. That's going into here now, right? No, I didn't do that. Okay. Now I've connected it. There we go. So now we've got 4 of those surfaces coming in here. And again, I'll hit double click the false start, this boolean here, in order to get the analysis running. And hopefully it'll oh, there we go. Great. It moved a lot faster than seeing something. All right. In Rhino, I'm going to hide that surface so that we can see the resulting analysis mesh more clearly. So this is a round surface. So you would expect that it would imitate. I guess what I'm trying to say is that this result here is something that you might have anticipated or expected. Let me jump over to I think the square one better. Sorry. Taking the time here. So I'm just going to change that input surface from those circular ones to the square ones. I've selected them in Rhino, and then I'm going to set multiple surfaces by right-clicking on the component from the drop-down menu. Churn. And then the way that this square is set up, the way that it's oriented is in such a way that south is actually this edge, and we're seeing more clearly exposure from the southeast, southwest, northwest, and northeast on each of these facades. I'll hide that. This will tell you how many hours something will receive sunlight during that week. So if you were to spend time to take a look at the results of this analysis and how it might distribute across the surfaces, you agree that you're seeing what you would expect. I wish there was, let's see a context. I'm sorry, I'm trying to think what would be like the cool next best thing to do. All right, so we got the sun hour analysis, and just to see what the impact of the shades that we're designing as we're running close to the limit. I'm going to jump over to the shading designer back here. What we have now is an analysis. This is showing us that in Gainesville, the two southern facades are getting many hours of sunlight given their orientation, and then the backside less so. We're only looking at autumn, so if we were looking at more of the year, we would see more variation among the different surfaces. I'm going to use the shading designer. I'm going to turn it off, make it visible so we can see what we're designing. I'll hide these for right now. Our test box, these are all being hosted on these surfaces on our test box. We have some inputs here where we can control the depth. Right now, this is 2 feet and some change. I'll do something a little bit more reasonable. I'll do a little 6-inch slats. The spacing between in Gainesville, we could probably go a little wider because the sun angle is much higher there. Shading angle is simply talking about how it tilts it up and down here, and then you can use this Boolean to try either vertical or horizontal versions. So I'm going to go get that back to 0. The shading. We've got horizontal shades. Should have baked that other analysis mesh. Make this a little easier to watch. Want to be able to see those surfaces, but not so, I don't want them to be so red and solid. So we're pulling those wireframes and previewing them as white. And we're going to come over here back to the sun hour analysis. Oh, there it is. It's still there. So let's save that real quick. See it? Oh. What I'm going to do before I run the next analysis is save the results here in the sun hour. There's its total sunlight hours. We've got 50,000 or 5,092. So we'll just keep that in our head. 5092. So as you may or may not. So in order to take a look at these shades, it needs to actually receive them into its analysis. The total sunlight hour analysis is still running. If we want those shades to be included, we just are going to drag the wire out to connect to the context geometry component. I like these little nodes that started to, I don't know when they came out, but kind of helpful. So hide these. We're seeing now our analysis mesh. Yeah, it's taking those, what we would hope for is that it's taking those shades and including them in its analysis. So you can see based on where they were located, the area immediately under it is has a little bit of coverage, while there still is a large portion of space in between that's receiving sunlight. In autumn in Gainesville, sunlight is not good. So you could do one of two things in this specific instance. We're gonna take a preview of this again. We could either go deeper or tighter together. So because I enjoy my view of the cypresses in my backyard, I'm going to keep the spacing the same and just make it overall deeper. I'm just gonna change it to 1. It's already running its analysis, and we'll see what kind of coverage we can get from shades that are 1 foot deep. All right, that's a lot better. Our corners are exposed because of the way that the component is building these directly on the surface and using normals of the surface to shoot it outward. So one would extend or perhaps turn that corner in order to provide the same coverage, or more likely, maybe there would actually be some structural elements and then an opaque corner. Yeah, so we've made some improvement as far as protecting ourselves from the sun during autumn. Let's see what it looks like during summer. Simply just using this import stat. It's a statistical file that pre-processed some data. It's taken a look at all year long and figured out which ones, or not all year long, but all summer long, and found out which ones were most summer-like. So we're looking at this now. I'm realizing now I've been looking at this. I think I need to change the colors. Looking at sunlight as though it were a bad thing, and when in fact it's a good thing, rather than radiation. But the two are very much the same. It's really just sunlight being delivered to a surface, and then the calculation or what's provided on the outside of it. Oh, that's pretty good. I mean, it's much less. It's 1/5. Well, I guess I changed it. The vectors and all of the ray tracing that's going on is going to provide you with the same type of graph or visual that we're seeing here. But what's helpful is the data that comes out that's associated with the mesh. So there's summer. What was it, 5092? So we've made it a foot deeper and we've cut it in more than half. So that's actually pretty effective. Well, it's got a half as long, and so maybe it's a linear relationship. So that's how you can quickly iterate with these shades. The individual cells on each surface have the data for them, or the amount of hours in which they receive sunlight is here in those lists, which is helpful. Any questions about this cell? I mean, now we're at 5:58. There's a bunch of other things I could show, but I don't want to, yeah, waste your time. Or yeah, if you have questions, I'd love to answer. All right, so this is the sun path. So this is where maybe we could have, although the sun path and the positions of those suns are shooting vectors out from those positions, and then where it hits these surfaces is where it's registered. We can build more geometry. I can't see. All right. We can build more geometry in order to indicate the context that's around, or to include that in our analysis. The thing I wanted to just finish with is just the conditional statement on the Sunpath. So the Sunpath diagram is being generated by pulling the weather data file and pulling together the weather data file and the analysis period and visualizing that path. I want to only see what hours or where the sun is when it's above a certain degree, when it's hot out, let's say. So I'm going to need write a conditional statement. In order to do that, you just need a little panel to provide some text. We are providing data from the, hold on, it's doing something. Oh no. Okay. So the Sunpath, the colors are coming from the dry bulb temperatures that are collected, and the dry bulb temperature is what we're going to filter through and isolate the Sunpath, the sun positions. I'm going to lock the solver so I don't keep causing it to recompute. A is going to be the variable that represents the temperature or the input data. I'm going to say greater than 80, which is Fahrenheit. So I'm going to need to convert the Celsius into Fahrenheit by going to Ladybug under extra. They've got different conversions. Let me get this window. F2C, so 80 to, oh, actually, I guess I can't do that. So, okay, so I'm going to instead take the input data, turn it into Fahrenheit, because it's not going to be able to take my text and turn it into Fahrenheit. I don't think it will know what to do with it. So in abundance of caution, I will put that data from the EPW file, convert it into Fahrenheit, from Celsius into Fahrenheit. This conditional statement, A greater than 80, it's going to be looking for instances in which that data is greater than 80 degrees. That text or the is just put right into the conditional statement. Right now, it's only looking at August, and August is or autumn. So it's likely not going to have a whole lot of days that are over 80 degrees. So I'm just going to throw caution to the wind and connect it back to the whole full year analysis period. And unlocking the solver, it's running, it's errored. It's errored because none of the hours meet the conditional statement. I can't. Oh, okay. I did this in reverse. So F2C, actually what I want is C to F. So Ladybug going from Celsius to Fahrenheit. I just took Celsius and turned it into more Celsius. So that's why that error occurred.
Unfortunately, I have to head out, but Jacob,
Yeah.
absolutely fantastic. Thank you for running through this, and I would very much be interested in grabbing a copy of the script.
Oh yeah, absolutely. We'll make it available on the Meetup page.
Awesome.
And cool. Thanks a lot for coming.
Yeah. Thank you. Have a great night.
Yeah, you too. See you. Yeah, and if anybody else needs to run, that's fine. I mean, you know, just wanted to get together and show something. Oh, there we go. All right. Yeah. So these are those, yeah, the Sunpath diagrams in which the sun is only over 80 degrees Fahrenheit. So neat. I don't know. Yeah. I can't figure out why they're all red. Why is that? All right. Well, yeah, anyways, There's so this is something that you can do with Ladybug, and that's pretty simple and easy. It does take a little bit of time to maybe get used to some of the logic that's behind Ladybug, and I don't know why this thing is running so terrible. My computer's had a bad day. I actually don't even know what it's doing right now.
This is great. Okay. I feel like you're able to successfully demonstrate what you were trying to demonstrate though, so that's good.
Cool. Yeah, it just doesn't seem that exciting. I mean, I don't have any cool floor plans to try it out on, you know, but maybe that's for the next class. We'll do some sauna kind of lily pad shapes. But yeah, I'm not going to try and keep you. If yeah, I appreciate you guys coming out and listening to this.